though, so. Can I use the same Go link? It's okay. Well, can I overwrite the Zoom link?
Yeah. Okay. All right, so I think we've gone live, but we haven't released the link to people yet, so people shouldn't be joining. But yeah, I'm gonna turn off my camera and like screen share a loading screen so people can't see us. And then when the time is ready, I'll introduce y'all. And then if you have any, you can just take it away. Yeah. Cool. Alrighty. Hello, everyone. Welcome to our second Blueprint Week event. My name is Lily, and I'm going to be moderating this talk with the MIT Rocket team. Before we get started, I wanted to remind everyone that if you are following along with this tech talk and have questions or comments that come up while we are going, feel free to put them in the Tech Talks channel on the Discord. And then at the end of this talk, we will have another Q&A session, just like we did yesterday. So make sure to ask your questions there, and then I will bring them up to our lovely presenters when we get started. But now for a quick intro, we're about to have an awesome talk by the MIT Rocket team. They're a group of students at MIT who works on building rockets with the goal of making it to space. We're really excited to hear what they have to say and really grateful that they're here with us today. So yeah, take it away. Thank you, guys.
Cool. Thank you very much. Let me share. Am I able to share my screen? Let's see. Get our beautiful presentation up here. So, let me make this small too. Cool. Well, welcome everybody. I hope you're having a great evening. My bad. Hope you're having a great evening. My name is Ellie Romero. I am a first-year student at MIT, planning to major in course 16, Aerospace Engineering, and I am the outreach chair for MIT Rocket Team. Medusa, do you want to introduce yourself?
Yeah, hey everyone, I'm Medusa. I'm a sophomore here doing aerospace engineering. I'm Rocket Team's vice president, and I'm a member of our aerodynamics sub-team.
Yeah, I should mention I am on the solid propulsion team on the rocket team. In today's presentation, we'll be going through a little bit of history about the team, what we've gone through, and what we just recently went through. And then we're going to talk about our future plans, and we're going to try to give you a brief lesson on the parts of the rocket team that we have the most experience in. So to begin with a little team overview, our goal is to develop the engineering, teamwork, and leadership skills of the next generation of rocket scientists. And this is because we are a completely student-run group. We design the rocket, we go request funds, we make all the parts, we assemble all the parts, we go test the system, and then we go across the country for launches. It's completely student-run, and it's a pretty extensive process. But we do this because we have a pretty large goal, which is to design, build, and launch a rocket beyond the Kármán line into space. If you don't know what the Kármán line is, it is the internationally recognized line. It's 100 kilometers above the Earth's, above like sea level, whatever, right? It's 100 kilometers up, and that's internationally considered as the line that divides Earth's atmosphere and space. And our goal is to make it up to space.
Yeah, so a bit of background on our team's history. For reference, I joined the team in fall of 2021, so I'm a little spotty on the history, but I'm going to do my best. So up until 2017, the team focused on competition rockets and built those and flew those in Western states. So our past rockets were Therion, Virgo, and Raziel being the last competition rocket this team flew, probably will fly for a very long time. And then beginning in 2018, that's when the team decided to shift the focus to build a rocket towards the goal of space shot. So we started the Hermes program, and the goal of this was just to see how powerful we can get our engines and really get good at launching it consistently at higher altitudes. That also brought along the rise of our staging demo program. So there were two of those, and that was the concept there was to prove that we could in fact build a two-stage rocket, because our current goal is to be the first collegiate team that launches a two-stage rocket to space. That brings us to our most recent project, Project Phoenix, which successfully launched this past January, which is very exciting. This project began in February 2020, so it was almost 3 years in development because, believe it or not, it's really hard to build and design rockets over Zoom, so COVID slowed us down a lot. But after a successful test launch in May 2022, we flew out to California, launched our rocket, and we made it to about 34,000 feet, which beat staging demo 2 for the team record by about a couple hundred feet. So that was really exciting for all of us. So like I mentioned, our current project, or our most recent project, was Project Phoenix. I just want to tell you guys a bit more about some of the mechanisms there. But before we do that, we have a video of the launch. So for reference, our rocket has 2 stages, a booster, the first stage, and a sustainer, which is the second stage. This footage is from a camera that was on the booster facing downwards towards the Earth, so you can see the motor ignite and watch the rocket go up.
Okay, hopefully you guys can hear everything. Fingers crossed.
This video is really boring until it's not, and then it gets very exciting very quickly.
For sure.
And right there, you can see that's our second stage lighting. So the stages have separated and the sustainer is now doing its thing, shooting off.
And then from there, it starts getting a bit choppy because we got something quite high. But that's the most exciting bit. We have another video of the sustainer, the top bit, but it's not quite as intriguing because you can't really see the rocket getting further and further away from the Earth. So yeah. Oh, I don't want to play that again. Let's switch.
And also all of our videos of our current launch and past launches are all on the MIT Rocket Team YouTube page. So if you ever want to see more, always go check that out. Some details about Project Phoenix. It was a 2-stage rocket that was originally designed to go to 65,000 feet. And then when we got closer to launch, our simulations were telling us that we would achieve around 45,000. Day of, we hit 34,000 feet. For reference, I know Ellie mentioned the Kármán line's 100 kilometers. For us Americans, that's 300,000 feet-ish. So we still got a long way to go to get there, but we still hit a new altitude record, so that was exciting for us. Some important features about Project Phoenix is that it features a passive staging mechanism. All that means is that we don't do anything to separate the stages. We let physics do it for us. So once you get to a certain height, the booster motor has stopped firing. The drag profile on the booster is going to be higher than the drag on the sustainer. So this is going to force the booster to fall off of the sustainer, and they just separate with nothing but aerodynamic forces. And then at some point, the booster parachute will just deploy and hopefully make it back to the ground safely. So our rockets feature a dual deployment recovery system, which means on the sustainer we have 2 parachutes, a drogue and a main. A drogue parachute is a smaller parachute that it doesn't light, that would be bad. It deploys before the main parachute, so it doesn't slow us down so much, but enough that we can deploy the main parachute safely, and also keeps us from drifting too far from the launch site, because if you were to slow down with the main parachute too far up, your rocket would drift so far away, and no one wants to drive 3 miles out to go find your rocket. The booster stage features 1 parachute, just the main parachute, because it is at a lower height. It doesn't need the extra help from the drogue. At our launch this past January, on the booster, the main parachute did deploy, but it ended up breaking off due to it would take too much force, or maybe the lines got tangled. We're still not entirely sure what happened, but we still did recover the booster stage successfully despite this failure, minus 1 fin falling off on crash landing. So that was pretty exciting. On past recovery failures, we've spent many hours digging out rockets from 4-foot, 6-foot holes because they end up burying themselves in the ground. So the fact that this didn't happen this time was a win. On the sustainer, the drogue parachute deployed. The main parachute ended up failing because some black powder, the explosive powder we used to actually deploy the parachutes, ended up getting wet before our launch. So the main parachute did not deploy, but the drogue was enough to recover it successfully. So despite recovery failures, which are the most common type of failure in any rocket launch you will ever see, we did recover both stages successfully. Our rockets also feature custom flight computers, which serve 4 main functions. They tell us height based on barometric pressure. they have GPS, so we know where to find our rocket. They tell the parachutes when to deploy, and they light the second stage of the rocket. All these computers and the code is written in-house by our wonderful avionics team. They do all the circuit work and all the coding right here in our lab. The last main component is aluminum fin can. The reason this is important is because it's a transition from previous rockets for us. So in the past, our team has used composite rockets, which essentially means they made them using carbon fiber layups. I believe Project Phoenix was originally designed to use carbon fiber, but the team discovered that it's just really hard to do reliably and successfully. And a lot of failures from past team rockets were fin failures. So they made the switch to aluminum, which is easier to manufacture. And we were able to create much stronger, more reliable fin cans, which have done a great job on the past 2 launches with Phoenix.
Okay, so on to Project Medusa, our new project. I don't have a picture of our rocket because we are literally just started this month, but we do already have some pretty good plans for it. We do want it to be a 2-stage rocket again because we want to build off the success of Project Phoenix. The goal of this rocket is to reach 100,000 feet at the minimum, hopefully above, which will get us to about a third of our way to the Kármán line. We're going to be spending this semester doing a lot of design work, prepping the rocket. That's quite customary. We usually spend 1 semester on design phase and the second semester on build phase. And so that's what we're going to be doing this semester. We're going to make some changes. The biggest one is that we're going to have much larger motors, which means that just the width of each stage, the booster and the sustainer, are going to be quite larger, so that we can have more propulsion to carry us even higher up. Instead of, in Phoenix, Medusa mentioned that we have like a passive separation mechanism for Phoenix, which means you just kind of let aerodynamics and physics do their thing. However, we want a more active separation mechanism this time. It's a little bit a more robust system, and it is a little more concrete, especially for the height we're going. And a third change we'll be making is we want to improve our recovery systems. We want to fix our parachutes, so hopefully we won't have to be concerned, or we'll be less concerned about recovery failure, because like Medusa said, that is the most common failure. And so this semester, we're going to do a lot of error analysis and find ways to improve Project Phoenix to make an even better upcoming Medusa. And then I'm going to take it away for our avionics. Like mentioned, Vanessa is on the aerodynamics team. And so she has a lot of knowledge and she would love to share with you guys.
Yeah, so real quick before I get started with that, I do just want to mention how our team is structured. So we run, we are a large project team that's divided into smaller sub-teams, which are aerodynamics, avionics, solid propulsion, structures. And then we also have a liquid propulsion team, which works on researching liquid propellant, but their engines don't fly in our rockets. So we're only going to talk about the teams we're more familiar with here today, but if you have questions about those other teams, feel free to ask those as well. Ellie, can you move up the slides? Yeah. Okay. So what the aerodynamics team does, we're all about stability. Our whole goal is to make sure we're flying in a straight line and not doing loop-de-loops in the air. So we design and manufacture our fins, and that's basically the gist of it. But there's a lot that goes into it, and to make sure we're stable, we need 2 key concepts, which are center of pressure and center of gravity, which I will go over on the next slide. Yeah, so some very basic physics is you have to know what the center of pressure and center of gravity are for any sort of stability to make sense. So you're probably familiar with the center of gravity, center of mass. It's defined as the average location of all your mass. Essentially, it's where you could balance an object, right? So if I have something heavier towards the left and something lighter towards my right, my center of gravity is going to be more towards the left. The center of pressure is the exact same concept, except it's area instead of mass. So if I have a larger area on the left and a smaller area on the right, my center of pressure is going to be closer to the left. And the center of pressure is important is because it's where all the aerodynamic forces are, you can approximate all the aerodynamic forces as acting at the center of pressure. And aerodynamic forces are your lift and your drag. And the center of gravity is where your weight is going to act. So for a rocket to be considered stable, the center of pressure must be below the center of gravity. So there's a few ways we can achieve that. Is one, you can make the top of your rocket heavier, right? So adding more weight will move the center of gravity towards the front, so that separates them. You can make larger fins, and that's because all aerodynamic forces are functions of area. So essentially, the larger area you have, the more lift, more drag you're going to have. So by increasing the area in the back, we move the center of pressure closer to the back. The other thing you can do is just make your rocket longer, which effectively moves your fins further back and your weight in the front further up. So that also increases the distance between the center of pressure and center of gravity. Now, obviously, all of these have their pros and cons, right? If you increase the weight in the front, you are making your rocket heavier. It makes it harder to fly. Making your fins bigger increases your drag profile, but it makes you more stable. So to decide the best way to design our fins, we have to optimize, and we use simulations. So we use a few different softwares to design our fins. Primarily, we've been using a software called RAS Aero. We also use OpenRocket a little bit, but that is more used for some of our smaller student projects. This semester, we're getting into learning some new softwares called FinSim and RocketPi, which let us get into more detail about how our fins are going to behave in flight. So essentially, we put in our dimensions of our fin: chord, span, root chord. These are all fancy words for different lengths of the different edges of the fins, right? You put in how big the rest of your rocket is, how much it weighs, how long is it, and you get output graphs like this. So I know it's really small, it's hard to see, but the x-axis is time, and the y-axis is a measurement of stability in calibers. A caliber is a really, really funny unit. It's a measure of how many body tube diameters are in between your center of pressure and your center of gravity. So if your body tube was 6 inches, and you had a stability of 2, there would be 12 inches between your center of pressure and your center of gravity. And that's the other thing. We do all of our work in customary units, so we're going to be talking in inches and all the fun American units during this presentation. But so this graph is telling us what our stability range is for different times in flight. And the way it does this is we also put in our motor information when we're running the simulations. So based on how much thrust the motors are providing and how fast we're going, it can tell us how stable we're going to be for any given fin shape. And for supersonic flight, we always want to have a stability higher than 2, which is here. So that means we're looking pretty good for the whole thing until we are, of course, falling and have entered the recovery stage, which is here. So the lowest point on our curve here is where we might have gone slightly less than 2. We believe is to what have caused a phenomenon called coning on our launch, and essentially all that means is, like, after separation, our sustainer stage started spinning in circles, which is not ideal because that's also how you lose altitude. If it's spending its energy spinning in circles, it's not spending its energy going up. But for the most part, we always had a stability over 2, which is great because our rockets do go over Mach 1. So they're pretty fast, so you need to be stable for that. And with that, I will hand it over to Ellie to go into our propulsion.
Fantastic. Okay, so I am on the propulsion sub-team, and we do 3 main things. We make our propellant, we make the housing units for the propellant, and then we burn it. So a little more specifically, we make our propellant in-house. We are the ones that are we've been working on this process, well, not me specifically, but the team has been working on this for just about over 6 years now. We make a propellant, and then as time goes by, we keep iterating it, making it better and better each time. The way we do this is a process called characterization. We do a lot of research and figure out what chemicals, what ratios we should adjust, and we make little adjustments. We test, we do simulations, and we repeat that process of testing, evaluating until we're happy with our results. From there, we've characterized a new propellant. That's what we're going to be doing this semester. We just launched our Project Phoenix. So with our next rocket, Medusa, we do plan to have a new type of propellant. The second and most safety considered thing is that we need to have very well-sealed containers for the propellant, because we want to make sure the propellant, when it burns, is only exhausting downwards. We don't want it exhausting up. We don't want it exhausting out. We want to keep the rocket intact. So that's another important part of our team. And obviously the most fun part is burning the propellant, because as you can see, this picture on the left is what's called a static fire. You're pretty much flipping the rocket upside down and you're setting it on fire. And what it's doing is on the bottom, there's like plates, which are attached to computers. And what it's doing is collecting data on average thrust, and it's a ton of fancy stuff. But the thing on the left, we do not launch that. We launch the stuff on the right when we flip the rocket the correct way. And this is a picture of the right of, I want to say, test launch for Project Phoenix, which was a year ago. But yeah, static fires are really fun. It's a really nice process. Fun fact, you can't do these tests everywhere. You're actually quite limited where you can go test. For static fires, we went into a fairly empty airfield. And for our Phoenix launch, because we're going so high, we ended up going around 34,000 feet, which is, by the way, about the heights that planes are flying. So there's only a few places where we're allowed to enter that level of airspace, which is why we drove all the way to California for our launch that happened last month. But a little more specific about thinking about our propellants, in the middle of the tube, depending on the shape that you have, that you choose to mold it into, you can produce different types of average thrust curves. And so here's another friend from the propulsion team drew this up. These are just different grain types. So this is, if it's all propellant except for, the hole, or one that has a star or a moon or finocle. Long story short, depending on the shape, there's going to be different burn rates. And since there's different burn rates due to different surface area, there's going to be different thrust curves, which is a type of force that will be produced. And so all these graphs are forced over time. And depending on what kind of situation you want, you choose a different type of grain. So yeah, that's kind of it for this picture. But here's a average sort of picture of the specs on our booster, which is the fatter part of the Phoenix rocket. And I'm not going to go into all this fun data, but a brief overview is that it tracks the peak pressure, which is a safety consideration to see if the aluminum tubing could withstand that amount of pressure. There's the burn time to see how long that propellant is going to be burning. There's the mass of the propellant, which is quite heavy. And then total impulse, which is created by just burning up the propellant. And then there's different class types. To be quite honest, I'm not quite sure. Like, we don't like make up the class types. Like, there's like a directory we can go to for those. But yeah, so here's just an average picture of pressure and thrust. But here's the fun bit. So the way that we construct the motor is that we have the propellant in the middle and then we house it. So on the sides, we have the liner and the closures. On the front, on the top, we have a forward closure because we don't want the propellant coming up. We want it only going down through the nozzle. So we have it nice and closed on the top, but on the bottom, we shape the nozzle in such a way that it's encouraged to come down in the way we want. So we stick that igniter on the bottom and we light the igniter. After that, it's going to start burning and it's going to go from the bottom up, which is what we want. but also depending on our grain geometries, we're probably going to cut, at least for the type of grain type that we use for Phoenix, it cut through the middle and then it went through the sides. And then head and ignition, because we had a 2-stage rocket, after this big booster started and finished burning, that leftover propellant on the top then lit the head end ignition. And then here's on the right, a more zoomed in picture of the head end ignition. And what's happening here is like, it's a very mini version, because what it's doing is that there's a little bit of propellant up there to light, burn, and then ignite the little igniter, the little blue igniter. Once that little blue igniter is lit, then the sustainer, the top part, the second stage of the rocket will go. And then we officially have a 2-stage working rocket. And so here's a little picture describing that process of after the boosters all the way burnt, it starts burning through the head end ignition, very similarly to the booster, and it's going to keep going through that burn process. The major components, like I talked about, we have our casing, which keeps all that propellant nice and safe and intact inside the rocket. We have a liner within the case, and then we have our propellant. And then at the top, we have the forward closure and the head end ignition, which is used to have propellant and burning come up when we want it to come up, basically. Yeah, and then we don't know quite a lot about avionics because, like I mentioned, we're not on the avionics subteam. However, because Blueprint is a little more computer science focused, we thought it would be a good idea to share a little bit about the avionics subteam. So, Vanessa, if you want to take it away.
Yeah, sure. So, yeah, avionics team, they are our computer people. We can build all the rockets we want, but we're not going to get any good info back if we don't have any good flight computers. So as I mentioned before, the avionics is in charge of telling us our altitude, telling us our location, and telling the recovery systems when to deploy. Those are our main components. And if you look at this picture here, the avionics bay, which is the capsule that contains all of this hardware, lives in a body tube that the structures team manufactures, and specifically in the mission package tube. So that's a structural side of it. But yeah, it's like I said, 3 goals: altitude, which is determined by pressure sensors, GPS location, and deploying the parachutes through black powder, that explosive mechanism.
Yeah, and the way we do that is because of all the anatomical units of the flight computer, such as the pressure sensors, which at a certain pressure, when you go up in the atmosphere, the pressure does change. And when the pressure changes to an amount that avionics team has determined, it tracks the altitude as you go up. And then using that data, it determines when things want to happen. And then I think for us, for non-avionics people, the most important part was the GPS, because it made the recovery system so quick. Most people during the launch, they're hiding in a bunker for safety reasons. I was on an away team, which meant I was safely away on a mountain. And so from the mountain, I was with the avionics team, and I was the one holding out antennas. And what I was doing was just tracking the rocket and helping the GPS data get sent into our computers. And so right when the rockets touched the ground, we knew exactly where it was, which made recovery such a pain-free process. And there's also a lot of other things like LEDs and buzzers, and most importantly, the central processing unit. But these are just basic and anatomical units of the computer.
Yeah, so this is a brief overview of how our parachute deployment system works. So, like we said, it takes input pressure. It uses that to determine height. It also has GPS to know where we are. At this point, this is where the avionics interacts with the structures team, because structures is in charge of its structures and the recovery units. So they work together to integrate parachutes such that the parachutes are attached to the avionics system. They're wired together, and when the computers determine that it's time to deploy the parachutes, they will turn on, send a little charge up to the black powder. It goes bang, as it says in the diagram, and theoretically, the parachute deploys. Yeah, so I think that's all for this slide. A project the team is currently working on, Project D.E.N.N.I.S, is our very own custom flight computer. It has not been the main flight computer for Phoenix. I don't believe it will be for Project Medusa either. It is an ongoing computer that's in development. I'm not super familiar with all of the specifications, but basically it is an attempt to make everything we do more in-house, because we do have to outsource some components for our avionics as of now, but with D.E.N.N.I.S, hopefully we'll be able to make a lot more parts and machinery in-house, which is always the goal. We want to make as much as we can ourselves, as much as we can as possible ourselves. So yeah, I know that was a very bare bones overview of avionics. As Ellie said, neither of us are part of that team. But if you're interested and have any more questions, all of our contact information is on our website, rocketry.mit.edu. That has resources to contact us, and so you can ask questions, and also links to our wiki where you can just go read about all of this stuff if you're interested.
Yeah, so with that, we are done with our presentation and we are totally up for a Q&A if you guys have any questions for us.
Alrighty. Thank you so much, Ellie and Vanessa. That was a brilliant talk, and I think gave a lot of insight into what you guys do on Rocket Team. We have quite a few questions in the Discord, so I'm not sure that we'll get to all of them, but I'll read some of the most popular ones and get a bit of a distribution. Let me see. So the first question, which I think, sorry,
we're gonna answer as many as we can. That is our goal. We got this.
All right. Okay, so the first one that I think people would be interested in is, how fast do these rockets go?
I don't have the numbers memorized off the top of my head. The answer is faster than the speed of sound. I want to say around Mach 1.2. Under Mach 2 for Phoenix. I think Medusa is looking like it will go slightly over.
Yeah.
Wow.
In the past, we've had one that's been closer to Mach 3, but that one was a mission critical failure mission. Just, it was too much for the rocket to handle. So we've gone about Mach 3, but it's quite hard to sustain.
Yeah, totally fair. The second question, which you guys did touch upon a little bit, was, do you need permission from the government to launch these rockets?
So
yes.
I can take a little bit. The answer is yes. Propulsion, we're making rocket fuel. So we have to get screened, and we need to get kind of talked to by ITAR, which tells us about who we can share information with, and just like talking about the process. That's we have to be kind of careful about specifics. We talked a little bit about airspace. The government has allotted certain areas for to be able to go that high into the air. So we do have to be very particular about where we do our testings.
Yeah, right before each launch, there's always a whole bunch of logistics trying to get waivers from the FAA. Basically, all that means is they've cleared us certain times and places that we're allowed to launch. And they said, okay, we're going to make sure it's safe here. There are not going to be any planes in the area. Go ahead. So there's always that logistical thing happening right before any big launch.
Awesome. Good to know. Someone else asks, does the use of larger motors make the rocket heavier? If so, how does this impact the design of the rocket?
So each motor has a different letter class, and most definitely a larger rocket makes a heavier rocket, because the most heavy thing is arguably the propulsive system. It is incredibly dense, incredibly heavy. If you're interested in chemistry, I recommend you check out our wiki page. But yes, it's incredibly heavy. And the way we deal with that, that's almost more of an aerodynamics question. Vanessa, do you have any input? I know we just scale up. Like, that's what we've kind of been planning on.
Yeah, sure, right? So I guess it's an optimization problem of weight versus power, but weight versus thrust. That comes down to doing lots and lots of good simulations and getting good data and seeing how high of an altitude we can go. For reference, we're looking to fly an N motor on top of a P motor. And what those letters mean, like Ellie was saying, they class motors by letter. And each letter in the alphabet has twice as much impulse as the one before it. So by the time you get down to N and P, you're pretty high up in as far as impulse goes. But yeah, it's a weight versus power problem as far as optimization goes. But the way motors are designed, you will get higher than you with a more powerful motor than you will with a weaker one. The weight just works out that way.
Awesome. I think this leads into the next question quite well, which is just someone asks, would you say making a rocket is all about balance? And then in parentheses, using design factors to balance different rocket factors.
Yeah, so 100% everything we do is an optimization problem, right? Like I work on the aerodynamics team. I would love for us to just have huge fins that are really like sharp and go way past the body of the rocket, but structurally that's a terrible plan. The structures team would want to have a huge fight with me if I wanted to do that, right? Like the avionics team would love if they could have a lot of space for their flight computers, but the structures and propulsion team are saying, hey, no, our motors are going to be this big and this is how much space you're going to have. Right. So everything you do is about optimization and making sure you can balance one aspect with another.
Awesome. Alrighty, we have a bit more of a technical question here from someone. They ask, which green type did you use for the Phoenix launch?
Yeah, so we actually use, let's see if I can go back to pictures. So we use a combination of, I know we use a phenocal on both. But I was told that we also incorporated baits into the booster. So you don't have to stick to one grain type, is kind of what I'm getting at. Phenocal is usually quite popular because you get wonderful surface area, which helps our burn rate. But yeah, that's what we did. We went with primarily a phenocal design.
Awesome. And then another more technical question, what language and framework is used to program the flight computers?
I think most of the work avionics does is in C++.
Awesome. Super cool. I think we have about 2 more questions, it's looking like. So the first one is, what is Project D.E.N.N.I.S being tested on?
Yeah, so the goal for Project D.E.N.N.I.S now is to fly it on L2 rockets. And what that means is the National Association of Rocketry, which is just an organization for all amateur rocket builders. They kind of moderate hobby rocket safety. So an L0 rocket is anything you can pick up at your local hobby shop, something you can launch in your backyard or like a local park, if you're familiar with like SD's model rockets, that kind of thing. An L1 rocket is a slightly larger rocket that requires certification to fly. And once you pass your L1 certification, which means you've designed, built, and successfully flown this larger rocket, you can now go buy higher power rocket motors, I think H and above. And after you past your L1, you can do an L2, which is essentially the same thing but scaled up. You now have to include a flight computer to get an L2. So we're looking at expanding the L2 program for our team members to be able to get these certifications. And we want to fly more of our avionics custom built stuff on the L2 flights, and that includes D.E.N.N.I.S.
Awesome. One last question. Thank you guys so much for all your time. We're getting a lot of really positive messages in the Discord, which I can send to y'all later. But the last question is, do you have some sort of aviation related program similar to the rocket team that focuses on airplanes?
We have a team called Design Build Fly, DBF. They are totally focused on building RC planes, and I do believe they do competition. So if you're interested in competition, you should definitely check them out.
Awesome. Well, thank you both. We've reached the end of the questions in the Discord. Again, we're getting lots of messages saying thank you for this awesome presentation, and I very much agree. if there are more questions in the chat, can I forward them to y'all and be a communication, share that between you
Yeah.
guys?
Yeah, for
our-
sure.
Our exec email is the fastest response time,
Yeah, I
If you
will
don't have
put
that, let me know.
also,
or, you know.
yeah, this is our website also. I just put in our Zoom chat. You can send that to people and they can find a lot of information and contact info there.
Amazing. Well, thank you so much. It's been great having you. To everyone who's watching on the live stream, we are really looking forward to seeing you tomorrow. Check your emails. We sent a lot of information about logistics. And if you have any questions, please hop on the Discord and ask us. We should have a pretty good response time there. So thank you again to the MIT Rocket team. And I'm looking forward to seeing all the hackers at Blueprint tomorrow.